Right. Guys, sorry we had a power cut. So we are back online again after a power cut. So where were we? Like fourth question, right? Yeah, I hope the drawing is still there. Is it? No, right? The whole thing is gone. Okay, doesn't matter. So we're gonna start it from the very beginning. So what did we discuss now? We discussed about one of the mixture method questions. Now the majority of the questions will be coming under the mixture method, right? So we have to have a better understanding about how and what the how and what happens in the mixture method. Guys, can you hear people? Malshi, Akif, Shashinder, Kishara, is Shiny there? Can you? Shiny is there. Okay, nice, good. So what happens in the mixture method? We'll discuss back again because like the last one was. Okay, now what happens in the mixture method? We mix two of the objects or two of the materials in two different temperatures. When the two of the objects got attached to each other, the one with high temperature is releasing the heat, the one with low temperature is absorbing the heat. So if none of the other things in the surrounding does not absorb any of the heat, or if there is no heat lost to the environment or for any of the other things, the heat released by the high temperature object is equal to the heat absorbed by the low temperature object, right? So heat released is equal to the heat absorbed. That is the simplest thing. Heat release equals the heat absorbed. That is what we are going to calculate there. So the heat release is mc theta of the heat release object, and the heat absorb is equal to the mc theta of the heat absorb object, right? Simple as that. So this is the metal aluminium. It had a temperature of 100 degrees of Celsius, specific heat capacity of 910, that is joule per kilogram per Kelvin, and the mass of 0.5 kilograms, right? And it is dropped into a water container which the temperature is 20 degrees of Celsius. Correct me if I'm wrong. And the weight is 1 kilogram, is that? Yeah, 1 kilogram. And the specific heat capacity is 4200 joules per kilogram per Kelvin. That is all, right? So we discussed the temperature is changing. Now the high temperature is reducing when the heat is released, and the low temperature is increasing since the heat is absorbing, and both of the objects come to an equilibrium. The temperature in the equilibrium, we call it the theta. You can take any of the symbols, it doesn't matter. We'll call it theta, right? So the theory here is energy release equal to the energy absorbed. Now the energy or the heat, right? Energy released by aluminium is equal to energy or heat absorbed by what? By water, right? Energy absorbed by water. So if I apply the mc theta here, the mass of the aluminium is 0.5. Now the energy release is mc theta of the object, and the energy absorbed is the mc theta of this object. So 0.5 kilograms, specific heat capacity is 910 joules per kilogram per Kelvin, and the temperature difference is the important part here. Now listen, the temperature is 100 to theta. It changes from 100 to theta. So it's 100 minus theta, right? And now this is equal to energy absorbed by the water. So the mass of the water is given 1 kilogram. Specific heat capacity is 4200 joules per kilogram per Kelvin, and the temperature difference is changing from 20 to theta. Now the theta is the highest temperature. So always remember, always you have to deduct high temperature. sorry, you have to deduct low temperature from the high temperature. So it should be theta minus 20, right? That is important. Theta minus 20. So now the only unknown factor here is what? The final temperature. That is what the question is asking for, right? Right. So you simplify it, you can find the final temperature. Now 0.5 into, right, 0.5 into 910 will be half of it, that is 455, right? And this you multiply it by 1, nothing happens. Come back to this, you're going to simplify the brackets. You have to multiply this twice, right? Multiply it by 100, then multiply it by theta. That will be this much, right? Minus 455 theta equals, you have to multiply the bracket again by theta by 20 twice. So 4200 theta minus 4200 into 20 will be, you multiply it by 2, this will be 84, 2 of the zeros are there, multiplied by the 0 that is left there is 3 zeros, right? So 84,000. Now what did you do? You should simplify the theta values separately and the other values separately. So take the theta values to one side. Now taking this minus theta to the other side will make it a plus. So 4200 plus 455, that will be how much? 4600 and now you are adding 4550, sorry, 455 to 4200, that will be 4655, isn't it? Yes, this much, right? Equals, take this minus value to here, that will be 45,500 plus 84,000. Can somebody tell me? You tell in numbers. 1, okay, okay, 500. Now you have to find the theta, right? So isolate theta. Theta equals this divided by how much? This divided by this 4655, right? So the answer is 27.82, right? Yeah, Celsius, right? So you did the same way. Now have this practice, draw a diagram before you are answering it, because the diagram will make it easy to understand and make it easy to approach when it comes to the answers, right? Because you will have to have all the details in the diagram. So when you are getting confused, you can look at the diagram and think of what's happening there, right? Easy way of doing it. Yeah. No, not in the structures. No. But when you are like me answering it, when you are doing the structures, you have it in your mind, or like you use a piece of paper, it will be easy. Because when you have an image, you get the flow, you know, the thinking flow comes when you have the image there. That will be the easiest way of doing it. Because always have an image. Always when you are memorizing something, the first thing that comes to your mind is a image. You try thinking of it. Like when you are memorizing, always first thing comes to your mind is image. Then after everything are coming, yes. So have an image. That's a good thing. Study with image. Have like me. Draw something when you are doing, especially in the physics, right? Even in the other things, right? So people online understood it, fine. Simplification and everything, okay. Yes, nice. So shall we go to the next question then? Right. An aluminium electric kettle has a mass of 900 grams and contains 1 kilogram of water at 20 degrees of Celsius. The time taken to boil the same mass of water is 5 minutes. The efficiency of the heating coil of the kettle. Assume that the specific heat capacity of aluminium and water in the relevant temperature range are 910 and 4200 respectively. Nice. Okay, so now this is the thing. The aluminium electric kettle and the water both gets the heat in this case. Do you understand that? The heating coil gives the heat, and the aluminium container or the kettle and the water, the both gains the energy or the heat, right? So they are asking for the efficiency of the heater or the heating coil, right? So the heating coil releases the heat, and the water container absorbs the heat, right? Water and the container absorb the heat. The heating coil releases the heat, right? So you have to find the efficiency of the heating coil. How do you find it? Efficiency means the rate of working or the rate of energy consumed, right? The rate of consuming of energy is the efficiency. So the efficiency of the coil will be the energy release or the heat release divided by time taken to release it, isn't it? Yes, the rate of releasing the energy will be the efficiency of the heating coil, isn't it? So how do you find the energy released by the heating coil? That is the energy absorbed by the water and the container, right? So what do you find first? You find the energy absorbed by the water and the container, because the details are given for that. So you find the energy absorbed or the heat absorbed by the container and the water, then you add them together, you divide by the time taken for that. That is the efficiency of the coil, right? Easy, right? So you have to tell me the values, huh? So let's say, as the question says, now there's a kettle, right, and there's a coil, a heater, right? Now the water is inside there. Now tell me the mass of the kettle. 1 kilogram. 900 grams. That will be 0.9 kilograms. And the specific heat capacity 910. Yeah. So 910 joules per kilogram per Kelvin is the specific heat capacity. And the initial temperature will be? Okay, now the initial temperature is 20 degrees of Celsius, right? That is 20 degrees of Celsius. And tell me the water, that is 1 kilogram, specific heat capacity 4200 joules per kilogram per Kelvin. And it's the same system. Since it's the same system, it has to be under the equilibrium. Get it? It has to be under the equilibrium, so it has to have the same temperature. Get it? Right? So the temperature of the water is also 20. Now understand that thing as well. So what happens once after the system is heated up? The temperature will increase. Would the aluminium or the kettle and the water have two different final temperatures, or would it be the same? It has to be same, because it's the same system. So at the end it has to come to equilibrium, right? So it has to have the same temperature. So final temperature is also same. So they are asking for the efficiency, right? And they are heating it to boil the water, isn't it? So the boiling temperature of the water is how much? 100. So the final temperature of both the systems will be 100 degrees of Celsius, isn't it? That is the final. So now the energy released or the heat released by the coil, heating coil, is equal to energy or the heat absorbed by water plus the container or the kettle, isn't it? This is the whole formula. Now you have to find the energy released by the coil. Now that will be mc theta plus mc theta of container and water. Now what is mc theta of the water? We'll put it first. 1 kilogram 4200 joules per kilogram per Kelvin, and the temperature difference will be 100 minus 20, right? So that is 100 minus 20, which is 80, right? So plus the container's mass is 0.9 into 910 joules per kilogram per Kelvin, that is the specific heat capacity, and the temperature difference is again the same, 100 minus 20, isn't it? Yeah. You have to simplify the whole thing. Can you tell me the exact answer? You multiply 4200 by 80. Yeah. 336. It's only for this one, right?
Yes.
336 plus 120. So altogether gives a complete heat of what? 4000. Now tell me numbers. 401. Oh. 520 joules. This is the complete amount of heat absorbed, and this is equal to the heat released by the coil, isn't it? Yeah. So you have to find the efficiency of the coil. Now the efficiency of the coil equals what? Energy over time. So the time is given how much? It takes 5 minutes to boil. So energy is this much, 401520 joules, and the time is 5 minutes. You have to put it in seconds. So that will be 5 into 60. That is 300. You divide it. What is the answer? 133. Nice. All right. 133. 8.4. This is the answer, right? Okay. Guys, is this clear? Yes, nice, Machi. So take the notes if you want. You did it this way, right? Nice, good, very good. And there will be more difficult questions. I'll be giving more. This is not enough. Nee. This seems too easy. Why not? It seems easy. I'll be giving more difficult questions. Huh? Right, take a fast note. You're done taking the notes, guys, online? People, you're still taking, right? Malshi done. Shiny? Shiny is still taking the notes. Yeah. I guess. I. No. Okay, different one. They are choti. No, not this one. Yeah. Now they can hear because they are replying. Shiny, put a text when you're done, no? Done. Shiny done. Nice. Yes. Yeah. Right. So that's so far all the exercise 1 questions, right? Yep. Now the change of state. Now this is about the latent heat of any of the materials, right? So state of like the change of state, what do you understand by that? What are the 3 states? The 3 states of matter are solid, liquid, gas, right? So the conversion between three of those phases will be the this what the change of state, which means if the solid is converting into a liquid, that is a state change. So that state change we call it as what? What do you call the solid converting into the liquid? Huh? You call it? What's that? That's something new. What do you call that? Yeah, I call it fusion, right? I call it fusion. And the liquid converting into gas is called evaporation. Good. So the reverse, the gas converting back into liquid, condensation. So the water converting back into solid is freezing, right? So those are the state changes, but we only consider in heat for the calculations only. Like for the calculations we are considering two of that, two of the latent heats we are discussing. One is the solid converting into liquid, that is the latent heat of fusion. We call it the latent heat of fusion. So we are calculating the latent heat of fusion. That is one thing. And the second thing is liquid converting into gas, which is the latent heat of evaporation. So we only have two. One is the fusion and the evaporation. That are the only two things that we calculate in the thermal physics part. That's all, right? Right. So what happens there? Now that is the next question. Now that you have to understand properly. Yeah. So what happens there in a a state change? What happens? So what happens when you apply the heat to an object? It heats up. What happens internally? Yeah, come in the terms of what we discussed it. When the heat is applied, what happens? Yeah. Yes. Kinetic energy increases, right? People online just may answer when I'm asking. Nah? So what happens when the heat is applied to an object? The kinetic energy of each and every molecules in the object is increasing. That is the vibration that increases, right? So the heat is there in a format of kinetic energy. So what happens when the heat is applied is the kinetic energy increases. The kinetic energy increases means more vibration. It can't stay at one place. It moves. Means it has more vibrations, right? It has more shear. It's shearing. The vibration is more. So what happens when the shearing is more or the vibration is more? The particles which were close together now are separating, right? So they're making much more of a gap because of the vibration, because everyone is moving. Let's say one of you are moving really fast, the others will move away, right? So the same happens in the particles. What happens when the more kinetic energy is there, when more heat is there, because of the vibration, the particles are moving away. That moving away of the particles, of the gap between the particles, makes it what? Expand, right? Makes it expand. That is what we call expansion. So when the heat is applied to an object, what happens to the object? It expands, right? It expands. So usually the temperature, now I'm coming to that point, usually the temperature we calculate using this expansion. So the temperature is there when there is an expansion, right? Because when it comes to the thermometer, what do we calculate there? The increased length of a liquid column, isn't it? It could be mercury or alcohol or something, that's a liquid column. So as the temperature, what we take is the increased length, isn't it? Because of the heat. Yes, yeah. Expansion happens there in railways as well. Now my important point is what? The temperature, what we measure is the length increase of a liquid column or the length increase of a alcohol or a mercury column. Do you understand that? So the temperature is somewhat the increase of length of a liquid column, right? So that means temperature is something that changes because of the heat. Usually in that liquid column is the length, isn't it? So the length increase that we like, what we discussed, the temperature is the length increase, isn't it? So it's an expansion, isn't it? Something relatively changing due to the heat, right? So it's a length increase. So it's a volume expansion in another way, because it's a liquid. So it's a volume expansion that we are calculating as temperature. Understood it? So if there's a temperature increase, that means there's a expansion as well. So if there's no expansion, that means no temperature increase is there, right? These points are really important because we'll have to use it, right? So if there's a expansion, there's a temperature increase. Get it? Or if there's a temperature increase, there has to be a expansion as well. And this expansion means the gap between the two of the molecules, no? Yes. So this gap comes to a certain point that they can't expand further, that they have bond, all the molecules have bonds. So at this temperature, the maximum expansion can occurs, right? Let's say in the water, the maximum expansion occurs at the 100 degrees of Celsius, right? That is the maximum expansion that the water can go. Afterwards, what happens? Now the bonds are cleavaging, or bonds are breaking, right? Now there is no further expansion now, right? Now there is no any further expansion, right? So now the bonds are breaking. The energy released by any of the energy source now is taken to break the bonds, not to expansion. So now we discuss, if there is expansion, there is temperature. Now what happens? At the 100 degrees of Celsius, the energy release is absorbed to break the bond, not to expand. Now would you expect a temperature increase in that scenario? No. So at the 100 degrees of Celsius, afterwards, no temperature increase is there. Get it? No temperature increase is there. But the heat is still absorbing. What for? To break the bonds. The liquid-liquid bonds, right? The liquid-liquid bonds are now breaking and forming gas-gas bonds, right? So the energy is completely taken to break down the bonds. Get it? Now that's what happens in the change of state, right? The energy that is released is completely taken to break the bonds. Because of that, the temperature is not increasing, or temperature is not changing. So at the boiling point of water, the temperature does not change. What happens there is, it remains at 100. So usually what happens is, the temperature is increasing when the heat is supplied, right? Temperature is gradually increasing from the 0 Celsius. The temperature of the water is increasing gradually to 100. Now once it came to the 100, it remains there. The temperature doesn't move afterwards, and the energy is still supplying though, right? So usually when the energy is supplied, the temperature has to increase, isn't it? But in this point, the temperature doesn't increase, only the heat is absorbing, but that heat is completely to break the bonds only. Get it? It is there to only to break the bonds. Because of that, the temperature doesn't increase. So that heat which absorbed without a change of temperature, get it? That heat which is absorbed without a change of temperature is called the latent heat. Get it? That is the latent heat, right? So the latent heat of evaporation are there, the latent heat of fusion are there, like two of those heats are there. So what happens now in the latent heat of fusion? A solid converts into a liquid without changing of a temperature. Get it? Right. So now come to the tute. Right. So we discussed these things, right? Here. Now the latent heat of fusion, the amount of heat required to completely liquefy a unit mass of solid at its melting point without any change in temperature, right? That is the definition. Shall we highlight few of the important points here? Amount of heat, right? amount of heat required to completely liquefy unit mass of solid, right? Unit mass of solid. In this case, like what do you call the unit mass of solid now? Unit mass of solid is what? Is simply what? Unit mass is what? How much of a mass? How much of a mass is a unit mass? It's usually 1 kilogram. If it says unit mass, that it means 1 kilogram. It means unit temperature. It means unit temperature means either it's 1 Celsius or 1 Kelvin. Yes. So it's a unit mass means 1 kg, right? At this melting point, right? And this happens in the melting point, isn't it? The state change occurs at a certain temperature. The fusion occurs at its melting point. If it is ice, that will be its freezing point, which is 0 degrees of Celsius. Yes, right. Without any change in temperature is called the latent heat of fusion, right? When the change of state of water is considered, ice becomes water at 0 degrees of Celsius under pressure of 1 atmosphere. Now highlight this as well. This is also important. Now this only happens at 1 atmospheric pressure or 1 atm of a pressure, right? Now do you understand this part? Now this is the latent heat of fusion. So the heat that it acquires to melt a solid at its melting point completed to a liquid is the specific latent heat of fusion, right? So there were few of the main points there as I wrote it, like as I highlighted up there. Amount of heat. Now if I convert this theory into a mathematical formula, it would be something like this, but this is equal to, what is equal to? Amount of heat, right? Amount of heat is equal to, right? Amount of heat is equal to what? Required to completely liquefy a unit mass of solid. Now unit mass of solid is also there. Does it have a unit there? Unit mass has a unit, right? Which is kilograms. That is per unit mass, isn't it? So per unit mass means it's a division, right? Per unit mass means a division, right? At its melting point. Now usually the melting point doesn't change. Yeah, at the fusion the melting point doesn't change, so it's not a variable, it doesn't change. So you don't have to consider the non-variables, right? If you are taking a formula, the factors in the formula has to change. That is why you are calculating. So you don't have to consider the melting point in this case because it's a constant, right? And without any change in temperature is called the latent heat. So only two were there. So amount of heat per what? Amount of heat per unit mass, isn't it? Amount of heat per unit mass is equal to what? Latent heat, right? Latent heat. I'll write it LH. So we symbolize it L, right? So if I convert this into symbols, right? Amount of heat you are usually symbolizing as what? Amount of heat. We symbolize the same in the previous ones, but Q. So amount of heat is Q. The mass is M. Now the latent heat, we'll take it as L. So the Q over M is equal to L. Now the latent heat is what? Q over M. Now shall we find the latent heat? Now this is specific latent heat, right? Specific latent heat units. Now that will be Q is measured in joules and the mass is measured in kilograms and the units will be joules per kilogram, isn't it? that is joules per kilogram, right? So if I isolate the Q, amount of heat that it takes is equal to mass into specific latent heat. Now this is the equation, one of the important equations, right? Can you write it here? Q equals mL. Write it in the box. Q equals mL, and define the terms. Q is amount of heat, m is the mass, and L is the specific latent heat. Yeah, done. If you want to take a note on this, doesn't matter, you take one note. You took it already, good. So it's not included there because it's not necessary, but it's good for the understanding. Finish? Yeah, right. So this is the graph. Now this graph shows you how the temperature changes with the heat applied, right? Shall I erase this now? Finish, right? Now the graph shows you how the temperature changes when the heat is applied. Now shall we label the two of the axes? Right, so take this one. Now this is heat, right? The applied heat, and this is temperature, y-axis. So now this is, let's say, water. This is actually water, right? This is actually water, and let's say now the object is at, now the let's say the ice, this should, if this is water, this should be ice, isn't it? Now minus 10 degrees of Celsius is ice. Now you are supplying heat to the ice at minus 10 degrees of Celsius. Now what happens here? The temperature of the ice increases. So it's increasing minus 10, minus 9, minus 8, minus 7, minus 6, minus 5. That is increasing the temperature, isn't it? The minus values are increasing when the values are decreasing, right? 9, 8, 7, likewise it's increasing, right? So the temperature is increasing. And when now there's a temperature difference, isn't it? If now temperature difference is there, so the heat absorbed by the ice, you can calculate it using what? Which equation? Q equals mc theta. So when there is a temperature difference, the equation you should apply is mc theta. So that will be mc theta, right? And when the heat is supplying, now the heat is supplying here, right? So the heat is increasing, which means the heat is supplying. And at a certain point, it comes to the 0 degrees of Celsius, which is the melting point of the ice. So now the fusion starts. What happens when the fusion starts? The temperature stays still, it doesn't move, because the heat supplied doesn't take it to increase its volume or any of the expansions. What does the heat is taken for now? Yeah, to convert into, yeah, the correct answer is to break the bonds, right? Now the heat is taken to break the bond instead of expansion. So because of that, the temperature does not change here. So now now still the heat is absorbing, isn't it? Because the heat axis is increasing its value, isn't it? So now how do you calculate the heat here? Which equation would you put? Q equals mL, because it's the latent heat. So in a state change, the ml should be applied to calculate the amount of heat that is absorbing. Get it? So this should be ml, isn't it? It should be ml. Now afterwards, after the complete mass of ice converted into complete liquid, this happens until the last final piece of ice converts to liquid, right? The latent heat is there until the last smallest piece of ice is there, right? So once the last small piece of ice converts into completely into liquid, then after only the temperature starts to increase again. Until then, until the last ice piece is dissolved, or not dissolved, fusion, the latent heat is still there. Get it? Until the last ice piece is there, the latent heat is there. So it's there until the final ice is converted into liquid. So now here it should be the ice. Now here this should be the water. This is ice in 0 degrees of Celsius. This is water in 0 degrees of Celsius. Get it? So afterwards, after all the ice is converted into water in 0 degrees of Celsius, again when the heat is applied, again the temperature is starting to increase, right? So after this point, the temperature is starting to increase, and let's write this up to the 100 as well, right? When it comes to the 100, now what happens? It's again boiling. Now what happens to the temperature after the 100? It remains still, right? Doesn't increase or decrease. So it remains still there. So for this part, you can apply what? MC theta. And for this part, you can apply what? ml, isn't it? So this will be, this is 0 degrees of Celsius water. Now when it comes to here, this will be 100 Celsius water, right? And this will be 100 Celsius this will be 100 Celsius vapor, isn't it? This is 100 Celsius water, this is 100 Celsius vapor. Yes, the steam, right? Now this is latent heat of fusion, this is latent heat of vaporization, right? Ekat liyum. This is latent heat of fusion, this is latent heat of vaporization. Right? Come to the next part. If Q is the specific latent heat of fusion, the amount of heat required to change a substance from solid to liquid without change in temperature, latent heat of fusion, is given by Q equals ml, thus L equals QM. Now it's the same equation, but Q equals L M, right? Same equation. So only the L changes when either if it is fusion, L has a different value, and if it is the vaporization, L has another value, right? Because depending on the state, change of state, and depending on the material, the substance, the L will change, right? Okay. Now, specific latent heat of vaporization, the amount of heat that must be given up for a unit mass of a liquid at its boiling point to change completely to the gaseous state without any change in temperature is called the latent heat of vaporization, right? So we discussed this, right? Right. Now this is one of the important points. Now go through these theories. You just read these. Yeah. There's another state. You called it triple point. There's a triple point sort of a thing. Now after the vaporization, no, there's a different state of me when a state take it convert you call it crystal state or something. When a state take it convert අපි ඒක යුනිවර්සිටි වගේ ගියාම පස්සේ ඉගෙන ගන්න පුළුවන්. ට්‍රිපල් පොයින්ට් ඒ වගේ තව කැලේ තියෙනවා මේක ගොඩක්. මේක ගොඩාක් ලොකුයි. හීට් කිව්වම පස්සේ. තව ට්‍රිපල් පොයින්ට් එකක් ඇඩ් වෙනවා. ඔක තියෙනවා. නෑ යුනිවර්සිටි ලෙවල් එකේ ඉගෙන ගන්න ඒවා ට්‍රිපල් පොයින්ට් එකට ගන්න right now come to this one. The basic differences between vaporization and evaporation of a liquid are shown in the table below. Now tell me vaporization and evaporation. Before that, shall we do a question? Come to exercise 2. Try first and second questions. That is from Q equals ml. And for the third question එකේ මෙන්න මේක චුට්ටක් දාගන්න. Latent heat of evaporation, sorry, vaporization of water equals 2.26 into 10 to the power 5 joules per kilogram. Make ඕන මේකට. Latent heat of vaporization of water is 2.26 into 10 to the power 5 joules per kilogram. Right. Done. Nice. Shall we come to the questions? Now, have you started studying as a group? No? At least you are studying by yourself alone. Don't smile, lah, because you don't have much time. So you have to do a lot of works, you have to cover a lot. Heat lesson එක දාන්න පුළුවන් හැබැයි නේ. Oh. Yes. Circular motion, work, power, energy, force. ඒ සෙට් එක නෙවෙයි. මේකත් දාමු. මේක චුට්ටක් තියෙනවා. Yeah. Oh. 2 hour paper complete. Seminar එකක් අපි web එකෙන් පස්සේ දාමු. Seminar එකක් ඕන වුණොතින් පස්සේ දාමු. ඒ කියන්නේ questions ටික discuss කරන්න seminar එකක්. ඈ? ඔව් paper එක ගොඩාක් අමාරු වෙකින් අපි seminar එකක් දාමු. calculations ටිකට දැනට. ඔව්. ඈ? paper එක කොහොමද discuss කරනවනේ? ඊට අමතරව seminar එකක් ඕන නම් අපි seminar එකක් කොහොමද කියලා බලමු. None? First 2 questions? First 3 Now just only do the first two questions, that is enough for now. So people online will be having a exam paper really soon. So get ready for exam. Force, work, power, energy, then the circular motion, and maybe the heat. I won't tell. I can include the heat because we have discussed so far. Because majority of the questions are there in like mixing method. Alright. Heat release equals to heat absorbed. Again, majority of the questions are coming. So we can include it, but we'll see. මේක අර චුට්ටක් deviate වෙනවා චුට්ටක් deviate වෙනවා. Then work, power, energy, force and circular motion are they are like relating to each other. මේකත් relate වෙනවා, but it deviates a little. චුට්ටක් deviate වෙනවා. Because heat is a different thing, isn't it? Done? Guys online, put the answers please. Yeah. ඒගොල්ලන්ට? They can, I guess, but I don't know they have allowed it. මේක තමයි. ඒගොල්ලෝ මේක ලව් කරලා නැතුව ඒක. බෑ ඒතකොට කරදරයි. ඒ අනිත් එක සමහර වෙලාවට ගෙදර කට්ටිය කෑ ගන්නවා මම ප්‍රශ්න තියෙනවා. No, you can put a text. Yeah. It's easy. Way better. Have you find the answers? Finish? So guys online, please put the answers in the inbox. It's easy, right? First two questions are easy. Third one, a little bit you have to think. Only a little bit you have to think further. Finish? Now the time is enough. At least people online just put the answers. what is the answer for the first question? The heat obtained when 1 kilogram of water at a temperature of 100 degrees of Celsius is completely converted to steam without any change in temperature is what? Dekha? Reaction is heat? Then what? Third answer, the specific latent heat. Correct, right? That is the can we yeah, it should be the specific latent heat of what? Of fusion, yes. Now the fifth one says the latent heat of fusion, that is correct, but now we can take both the answers correct, but this is the thing. If it is specific latent heat, the specific means 1 kilogram. Get it? Specific means 1 kilogram, right? It's the same like specific heat capacity. The heat capacity is there. Can we remember? The heat capacity is per the whole object, and it becomes specific because it considered 1 kilogram. So specific is 1 kilogram. So it has to have the specific, because otherwise it would be just the latent heat. So here it considers the 1 kilogram, isn't it? So it should be specific, and since it says the 100 degrees of Celsius converting the steam, so it should be the vaporization. This is fusion, man. Yeah, this is fusion, it's vaporization. So it should mention the specific latent heat of vaporization. The whole answer should be that, but the most correct answer is what? Specific latent heat. Yeah, so the most correct answer is 3. The specific latent heat. If it was given like 2 of the answers, the specific latent heat of vaporization, that will be the most correct answer. Yes, that will be the most correct answer, right? The specific latent heat, right? Come to this one. Specific latent heat of vaporization 9900. Get the same answer, 9900. Is it? No? You got something else? Yeah. What about the boy? Get a different answer, the same answer. Fifth answer. Okay, let's see. How much heat is required to completely melt a block of ice with a mass of 30 gram at, this should be 0 degrees Celsius. The specific latent heat of ice is given. Now that will be Q equals ml, isn't it? Q equals ml. Now the mass is 30 grams, but you can't keep it in grams, can you? It has to be kilograms. You divide 30 by 1000. Yeah, so 30 by 1000. Then you multiply by the L. L is 3.3 into 10 to the power 5. You took it differently. It's not 105. That is 10 to the power 5. You took it differently. Bro. It should be power. 10 to the power 5. Usually it gives 10 to the power 5 values. Yeah. So you multiply it. Now 0 to 0 can cancel out. 2 of the zeros are there. That will be 3. That will be 9.9 multiplied by 10 to the power 3. Now Shiny is correct. 9900 joules. So this is my mistake in Visalan. This should be 10 to the power 5. That is power 5. 9.9 10 to the power 3 is 990. Sorry, 9900. The answer is 5. Answer is 5. Yes. Good. Shall we come to the question? Now you try the question number 3 at home. All the details are there, right? Yeah, all the details are there. So do it at home. ඒක චුට්ටක් you will have to think. හොඳයි. ඒක හිතන්න mixing method එක තියෙන්නේ. Latent heat එකයි specific heat capacity එක දෙකම ඒකේ සම්බන්ධ වෙනවා. Question එකේ. So think a little bit. Right, now come to this point. What is this point? Vaporization and evaporation. Are those two things or are they the same thing? Vaporization and evaporation. What do you think? The same thing or the two of the things? Two of the things. That is why they are in two columns, right? Otherwise I have put it in one column, yes. So yeah, that is two things. So what is the difference? Vaporization and evaporation. Okay. That happens naturally, occurs naturally. The vaporization we have to give heat. Yeah, so it happens artificially. We have to give it, right? Artificially means in the sense like we have to apply the heat for it. Yes. So yeah. So we somewhat know the vaporization, because vaporization we do it at home. You boil the water to make the hot beverages, like tea or plain tea or anything. Yes. So what do you do there? To make it evaporate, you apply the heat and you take the temperature up to how much? 100 degrees of Celsius. Then the water is evaporating, isn't it? So that's the vaporization, right? So the water is vaporizing when it comes to the 100 degrees of Celsius. That is something we know. But the evaporation is something different. Evaporation doesn't happen increasing it up to 100 degrees of Celsius, but still the water is going to the atmosphere, isn't it? So how does the water goes to the atmosphere without taking the temperature up to 100 degrees of Celsius? How does it happen? Now that is the important thing, right? Now try to understand this theory, right? So let's say there's a pond, right? Sort of thing, yes, but doesn't come to the 100 degrees of Celsius. That is the thing. So usually in vaporization it has to come up to 100 degrees of Celsius, but in evaporation it doesn't have to come to 100 degrees of Celsius to go to the atmosphere, right? Can happen in any temperature. Now this is how it usually happens, right? So this is a pond of water, right? So water is here. Now this is water, right? So water is there as H2O molecules, right? Water is there as H2O molecules, isn't it? Water is simply H2O. Right. And these H2O molecules are dynamic. What do you mean by that? H2O molecules are dynamic, which means it's moving. It doesn't stay still in a liquid. If you take a water glass, the water molecules inside it, it doesn't stay still. Do you understand that? It doesn't stay still. The water is always moving. It moves because it's a liquid. It can move because much of the space is there. So it's moving. So that means the water molecules are moving, means it contains what? Which energy does it contain when it's moving? I'm not saying vibrating, it's moving. What energy does it contain? A moving object contains? A moving object contains what? Which energy? Kinetic energy, bro. Oh. Just think in simple terms. Don't think it really deep. No, it's simple, right? So moving object or the moving H2O molecule has which energy in it? Kinetic energy. So the collective kinetic energy of all the water molecules is its which energy? We discussed this. The collective kinetic energy is heat. Yes. The collective kinetic energy of this each and every water molecule is the heat of the pond. Yes. So let's say the collective kinetic energy of each and every molecule of water or the heat is 100 joules, right? Is 100 joules, right? So now this is what happens in the evaporation. Now you listen what you're doing, arts, listen to this, right? So what happens here now? The water molecules are moving randomly with its kinetic energy, and it's one of the water molecules hits one of the water molecules in the edge. Now let's say this water molecule is coming in a random movement and hits this water molecule. And what happens to this water molecule? It escapes the water, absorbing the energy that it was given. Get it? Now this water molecule is escaping when this water molecule goes and hits the water molecule in the edge. Now what happens? It escapes there. So water molecule comes here. Now it escaped, right? So when it escaped, it took the energy, isn't it? Otherwise it can't escape, right? So it took the energy. Which energy did it took? The kinetic energy, isn't it? So this took a little bit of energy, right? So since it took a little bit of energy, the energy that it took was the energy inside the pool, wasn't it? We call it the internal energy as well. So the internal energy in this case is heat or the kinetic energy, right? So it took a bit of the internal energy and escaped. Now what happens to the complete or the total energy of this pond? Is reducing. Get it? Is reducing, isn't it? So the complete energy is reducing, which means now let's say it took 1 joule when it's escaping. Now the complete energy of the pond is reducing up to down to 99 joules, isn't it? Get it? Now if few of more H2O molecules escape like this, now this is like in a bus. Let's say you're in a completely packed bus. So no any of the other passengers can put there. It's completely packed, saturated. And you are trying to squeeze someone inside. What would happen? If it is saturated, someone will jump out from the front. If you entered from the back, somebody the same size will jump out from the front, right? So that is the saturation. Get it? So now, what was I to tell now? So it's now the same thing. So now when this one is moving inside, what happens? Yeah, the one in the edge will go out, right? When it hits the edge, it will go out, right? And when it is going out, it takes the energy with it. Yes. So the internal energy of the system or the pond will reduce, right? So when the internal energy, let's say like 3 or 4 molecules are escaping likewise, so the internal energy will reduce. Let's say 5 molecules escape, so now the internal energy is 35 joules. Get it? So what does this mean? The internal energy or the kinetic energy of the pond is now reduced, isn't it? So the kinetic energy is reduced means the heat is also reduced, right? The heat is also reduced means the temperature is also reduced, isn't it? Get it? The temperature is also reduced. So due to the evaporation, the temperature of the system, what happens? Goes down. But in vaporization, it doesn't. It stays in the boiling point, isn't it? Get it? So now in the evaporation, the complete energy of the system is reducing, right? So the temperature is also reducing. So this was known by the old ancient geniuses. So they made sort of an instrument, right? Sort of an instrument that they can cool things, something like water. They can cool water using this instrument. What is the instrument? Ancient didn't make the fridge, bro. Ancients. Is it really the fridge? No. Which? Huh? Ancient made this instrument to make the water cool. Yeah, the clay pot, isn't it? You call it the clay pot, yes? Kali. The kali is the clay pot. Yes. So they made the clay pot, knowing this theory, not the exact theory, but they knew something, right? So this is what happened in the Gurulet, or the you call the clay pot. Now inside the clay pot, right, there are small macro holes, right? Very small macro holes. Macro holes means very tiny holes that only like one water molecule can enter. Very tiny holes, right? So through these macro holes, now let's say there's water inside. Through these macro holes, what happens is water molecules are escaping one by one, right? Water molecules are escaping one by one, right? When the water molecules are escaping likewise, what happens? The evaporation occurs. In the evaporation, what do they do? When they are escaping, they are taking the internal energy with it. A small amount of internal energy is taking with them, isn't it? So when they are evaporating, what happens? The internal energy is decreased, so the heat is also decreased. Now because the heat is decreasing, the temperature is also decreasing. So the pot, the clay pot water is cooler than the normal water. Get it? So it happens because of what? Because because of the evaporation process, right? The evaporation happens with the energy. Yeah. Because if you keep, like if you touch the surface of a clay pot, what would you feel? A bit of a wetness is there. Why? Because the water is escaping from there. From the surface, it's escaping, right? So because of that, the water level will go down in a certain period of time. So it won't go much lower, but a small amount is reduced, and due to that small amount of reduce of water, the water is cooling. And think of that scenario of the whole thing. No, it's beautiful, isn't it? The physics is beautiful, isn't it? So the water level is reducing and the internal energy is reducing. So the water is escaping, and because the water is escaping, the inside water or the system is cooling. Now you can use it for something, isn't it? So you are going to be the engineers, and you all want, like you are wanting to likewise, Metigeval. No, maybe Metigeval. Oh, you understood the whole concept, no? So you can use this physics to make naturally cooling systems without any power consuming. Metigeval, okay. I'm not telling about the Metigeval. Even Metigeval are really good. Apart from the Metigeval, using the physics concept, you can do something new. You can build something new. A natural cooling system without any power consumption would be beautiful, isn't it? And maybe that's why they didn't think it this way. They got the the experience, one thing, and hopefully they had this Eastern wisdom as well. This Eastern sciences were there, like it was different from this, like Pirit Vatura, Pirit water, holy water, like two different things, but is something that giving energy to the water, isn't it? So they knew something about the changing of energy and flowing of energy and everything, but it's a different science though. The Eastern science is a different science and it has a very deep depth, and the Western science is another thing, and two are like I don't know if people want to combine it together, like they are going in two parallel lines, yes, but in some cases they are aligning, yes, true, but in some cases it's not. But two of the sciences are really beautiful, and I like much more Eastern science than the Western science, for real, because it has more beautiful things than the Western science, because it comes with a huge it comes with a huge the cult. It's a huge culture. Yeah, the Eastern science made a huge culture, very huge culture. Western science did as well, but it's a bit of a more rigid, some sort of a solidity is there, like it's too hard, if you understand it. It's too hard. It's not. Huh? Yeah, too theoretical and yeah, kind of like me straight lines. Doesn't have any. Yeah, no curves likewise. So yeah, that's it. So come to the theory. Yes, so this is vaporization, this is evaporation, right? Now we'll discuss this. The boiling of given liquid under a given pressure occurs at a given temperature, right? So this happens under a given pressure and a given temperature. Now usually the given pressure is 1 atm or 1 atmospheric pressure, and the temperature of boiling is how much? 100 degrees of Celsius. Now you have to understand this as well. I'll come to this point as well. Now listen. So about the pressure, does the pressure affect the boiling temperature? Does the pressure affect the boiling temperature? It does. It does. It does. Now you go to Norelia. Now before that, how does the pressure affect the boiling temperature, or how does the pressure affects the vaporization? Now this is how it happens. Usually the atmospheric pressure is the pressure by the air, so it applies to everywhere, right? So now in a water surface, the pressure is applying directly to its surface downwards. Get it? So now this is the atmospheric pressure P0, right? So the water can't escape because the air is pressuring it downwards. Get it? The water can't escape because the pressure is pressuring it downwards. The atmospheric pressure is pressuring it downwards. So we have to apply the heat to increase its, what happened there? Right? We have to apply the heat to increase its vaporizing power or the kinetic energy. Right? When you are applying the heat, the kinetic energy is getting more, and when it comes to a certain point that the liquid gives a equal pressure that the atmosphere gives. Get it? The liquid gives a equal pressure that the atmosphere gives, and that is only it can escape. That is when the vaporization happens. Get it? So it has to give the equal pressure. So for that, the kinetic energy has to increase. Get it? So let's say if now for that, the certain amount of heat has to be given. Depending on that certain amount of heat, there's a certain temperature that it boils. Get it? So let's say the pressure decreases. So the heat that it takes to escape would be less or more. Back again. If the pressure is low, the heat that it takes to escape or vaporize would be less, because it's not pushing the water molecules down much more. So the energy that it takes to escape to the water, to the gaseous states or the atmosphere will be less. Get it? No, change it. Oh, it changes. Then make a, now this is 1 atm. Now if the pressure reduce than 1 atm, the energy that it takes to escape will be less. That means less heat is taken to vaporize. Less heat means less temperature, isn't it? So the boiling point will reduce. Get it? So if the pressure is less, the boiling point will go down, and the heat that it contains inside will be also less, isn't it? So that is why when you go to Norelia and certain areas like the mountain areas, the pressure is low and the water escapes before 100 degrees of Celsius because of the low pressure. So less heat is contained inside the water. So you can't boil sometimes the potatoes or whatsoever the things you boil, you can't boil it. Why? Before it gets boiled, the water escape. It's hard to boil there. Maybe 98, 99 or something. So the Alagovio there, they can boil the potatoes, no? Because it's escaping before it boils, because it's temperature is the boiling temperature is reduced due to the less pressure, right? So how do you overcome this? They came up with a simple thing. What? To overcome it. Or let's say you have something that you can't simply boil. You can't easily boil it. What would you do at home? Let's say you have some sort of a vegetable, you tell it a different name. That what is the name of that cooker? The pressure cooker, yes. You take a pressure cooker. What happens there in a pressure cooker? You seal the lid. What happens when you seal the lid? The pressure is increasing inside it. So when the pressure is increasing, what happens? The the temperature that it gets boiled is increasing. That means that the inside of the water, it contains more heat than previously, isn't it? So it contains more heat because the pressure is more, it can't easily escape. So the temperature is also increasing, which means it has more heat inside the liquid now. So it can easily boil something. Get it? So that we call a pressure cooker. Yeah. So that's the reason you are using a pressure cooker, right? So pressure cooker increases the pressure so that the boiling point is also increasing. Now that is what I wanted to make you understand about what? The boiling point changes with the pressure. Yes, because the 100 degrees of Celsius is the boiling point of water, but under 1 atmospheric pressure only. Get it? The 100 degrees of Celsius is the boiling point of water, but under 1 atm pressure only. Get it? It can atmosphere උඩට යන්න යන්න අඩු වෙනවා. Yes. උඩට යන්න යන්න pressure එක අඩු වෙනවා. Space එකේ atmospheric pressure එකක් නැහැ. atmosphere එකක් නැහැ. So no atmospheric pressure is there. ඒකේ vacuum එකක් තියෙනවා. vacuum pressure එකක් තියෙනවා. අඩුම atmosphere එක I can't tell it exactly like that. Lithos තියෙනවා. layers තියෙනවා. උඩට යන්න යන්න no. Above from that. Right? So anyway, you got the theory, right? Understood it? Nice. So the boiling point depends on the pressure. Yes. So that's why it says the boiling of a given liquid under a given pressure occurs at a given temperature. It happens in a certain pressure, correct? And a certain temperature. Yes. Right. But the evaporation doesn't happen the evaporation doesn't affect by the temperature. It get affected by the temperature, but doesn't have a certain temperature to escape. Get it? It happens in every temperature. It can happen in every temperature because it takes the internal energy and goes by itself. So it can happen at any temperature. So the second, the temperature of a liquid remains constant at its boiling point when heat is supplied until boiling is complete, right? So this boiling temperature remains constant that we discussed until the last final drop of water is evaporated. The temperature doesn't change, it remains constant. But in the evaporation, if no external heat is provided for evaporation, some particles will absorb. Make a evaporation. This is evaporation. Some particles will absorb energy from the liquid region and turn into vapor that we discussed, right? Right. Third, during the boiling bubbles, right? During the boiling, bubbles and steam escape from everywhere, including the interior of the liquid. So that is a visible process. Now, vaporization is a visible process. You can completely see it happening, right? But the evaporation, you can't see it happen, right? If you look at a water surface, you can't see the water molecules escaping in evaporation. So hence the liquid cools in evaporation. Vapor escapes only from the surface of the liquid. The evaporation happens only in the surface, but vaporization happens everywhere in the container, isn't it? So it goes everywhere, like bubbling happens everywhere. Yes. So the speed of boiling does not vary with the temperature, right? That means the boiling point can change, right? It can go down to 98 degrees depending on the pressure. It can go up to above 100 depending on the pressure. Though the boiling point changes, the rate of vaporization, the speed of vaporization doesn't change, right? The boiling point can't change the vaporization. Get it? Temperature change වුණාට vaporization වෙන rate එක change වෙන්නේ නැහැ. It happens in the same rate whatsoever, like though the boiling point went down or though it went up, the rate of vaporization will be same. It will dance the same rate. Though the temperature go high or down, doesn't matter. Dance the same rate. When it starts to evaporate, will do the same rate, won't change. But when it comes to the evaporation, what happens? When the temperature is increasing, what happens? The internal energy has to increase, so the vaporization is also increasing. Get it? So the evaporation is depending on the temperature, because temperature is increasing, evaporation is also increasing. 5. The speed of or the rate of boiling does not depend on the surface area of the liquid exposed. Now, if you take a large container or a small container with a large area and a small area, when it starts to boil, the rate will be still the same. The speed at which the water is escaping will be same. It doesn't depend on the surface area. But when it comes to the evaporation, the area really affects. Why? Now, I'll tell you an example. Let's say you are taking a glass of water to your room and you are putting the fan on, and you are taking another equal volume of glass to your room and you are spreading it on the floor with a large area, and you are going to sleep and you are waking up the next day and you are looking at the water glass, you don't see anything escape there. But when you look at the floor, nothing is there. Why? The surface area affected the evaporation. Yes, because more the surface area, it will evaporate faster, because the evaporation happens from the surface, isn't it? So the larger the surface, more it can escape, right? Right. The speed of the boiling does not depend on the wind. The wind can't affect the boiling, right? When it starts to boil, like it's with a huge energy, right? We heat it up to 100 degrees of Celsius, so the wind can't affect that. But when it comes to the evaporation, no, it's an innocent process. Doesn't have any of the heat. So the wind can affect it, because the wind takes the surface water with it. So the water molecules are escaping with the wind. Get it? So the evaporation is affected by the wind as well. Got it? Nice. So that is about vaporization and evaporation, right? Okay. Now the next thing to discuss is method of heat transfer. Now the next week we'll discuss the conductivity, heat conductivity, right? I'll just explain the method of heat transfer first, and we'll come to the conduction and we'll finish it there. Fine? Yeah. We have a few more minutes to go, so we'll discuss a bit. Huh? Right. So now this is the basic. So the heat is transferring in 3 ways. How? Conduction, convection and radiation. That is how the heat is transferred from one to another. So now the real thing is the heat, the actual heat, the original format of the heat is actually the radiation. Now try to understand this. Huh? The actual form of heat is the radiation, which is the electromagnetic wave that we called as infrared. So infrared is the actual heat, that is a wave, because energy is always in a wave format. Energy is always in a wave format. So the actual heat itself is this infrared or the electromagnetic wave, right? So that is radiation. So radiation is the original form of heat. Get it? Right. So then what is conduction and convection? So the radiation happens, let's say from the sun. The sun emits the radiation and it comes to the earth, doesn't matter if there's a media or not, because the original format doesn't care about the media. Though if there's a media or not, it can still propagate. Get it? It can still go. It can still move. So it comes to the earth and it meets a surface, right? Meets a surface. Let's say a solid surface. What happens to there? Let's say our people are staying in a line. Now our people are there. Now there's Shiny there, Yuhasa there, Diana there, and yourself there. Now everyone is there, right? And let's say this is the heat, right? This is the heat. So I'm giving the heat to one of the persons. Listen, I'm giving the heat to one of the persons. So he is absorbing it. So its temperature is increasing. The temperature of the next will be less than it. So now what happens? Now this heat goes to the next one. So it's the same heat, right? This. So it is firstly absorbed by this. So it goes to this, and after it goes to this, after it goes to this. Likewise, the heat is moving from the one is next to it, right? The heat is moving from one to the next to it, because there's a bond, right? Because of the bond or the contact of the particles, the heat is conducting. That is called the conduction of heat. So heat is inside, right? Heat is inside. It's moving inside as an electromagnetic wave, but it propagates using the particles which are attached to each other. So that is how the conduction occurs. So for a conduction to occur, the particles has to stay sticked, stay attached. So usually the conduction happens through the attached particles, right? The conduction occurs through the attached particles. So usually the conduction occurs more in solid particles. Get it? So the more the solidity, more the conductivity there, because it has to move through the attached particles. Get it? So conduction happens through the attached particle, and that conduction is the heat, not the particles. Particles are the media. The actual heat which is conducting is the electromagnetic wave. Get it? Now that is like your set of people are there, and I'm giving you this, heat which is the pen, and Diana is giving to Yuhasa, Yuhasa is giving to Shiny, Shiny is giving to you. Likewise, the heat is moving, going to this one, he is going to this one. Likewise, the heat is moving. Now this is the heat, and that movement through the attached particles is the conduction. Get it? And now what is the second thing? The convection. Now convection is a different case. Let's say there's only two people there. Let's say Diana is in the one side and Shiny is there in the other side. Now when all the other things are the space, that is whole space there, right? So you can easily move. So when the energy is applied for one person or an object, what happens there? What increases? When the heat is applied for an object, what is increasing? The kinetic energy increasing, which means the vibration is increasing. So now Diana is absorbing much more of a heat. So what happens to the Diana? Her kinetic energy increases because there is no other particles keeping her rigid or contact to the surface. She can freely move. Now what happens to the particle or the Diana? She is getting excited, isn't it? Because she is absorbing the heat, she is getting excited and she starts to move. What happens now? No, like everything else there is the space. Now she starts moving, yeah, with the excitement. So now what happens? Now that movement of herself or the particle with the heat energy inside it is what? Is convection, right? The particle moving with the energy is convection. Get it? Now Diana is moving with the heat now. Now half of Diana was left, right? Now Diana is moving with the heat, and all of a sudden randomly is getting contact with shiny. Now what happens here? The energy is passed to the shiny. Now what happens to shiny? Shiny happens the same thing. What? She is in the space, like much of the space is there, nothing is connected to her. So she gets the energy, she gets excited, she her kinetic energy increases, she is moving back again to another place and gives the energy to another place. And if Yahasa meets on the way, contacting with the Yahasa, passes the energy, then again the Yahasa goes with the energy to another place. Oh, එයාගේ energy release වෙනවා. ඔව්, එයාගේ excitement එක නැති වෙනවා. කියන්නේ එයාගේ energy එක කලින්ට වඩා අඩු වෙනවා. Right? So do you understand this now? So inside a convection, now the particle moving with the energy is the part which we call the convection. Get it? And inside the convection, there's a what? Bro, no. Now how do you pass the energy to the shiny? You have to touch each other, isn't it? So that is what? The energy pass through a contact of the particle next to you is conduction, isn't it? So when you are touching her, I'm not saying that way, right? You don't smile. So when you are touching this particle with that heat, what happens? The energy is passed through what? Through conduction. So inside the convection there is conduction as well. Get it? So you be asking these questions, like there's one past paper question, a coolant system of a engine was given, and the questions were asked like how the energy is flowed inside the liquid or inside the coolant, and how does the energy is passed from the liquid to the metal surface and from the metal surface to the atmosphere. You have to write it using the conduction, convection and everything, right? So you have to have the proper knowledge how it passes, right? Otherwise you can't tell it. So inside every convection, conduction is also there, right? Nice. So now heat conduction we will discuss the next day. So radiation is the original format of heat. It doesn't have to have a media, and the two of the other things are the convection and conduction. Convection and conduction has to have media, right? Otherwise it can't occur. Get it? Nice. Right. So we'll finish the class for today. We'll discuss the conduction next week. We'll have to do some calculations as well and do the homework that latent heat question, do it. Right. So we'll see you guys the next day. People online, see you guys the next day. Adios.